I want to introduce an important concept for rotation by thinking through something we never actually did in class during conservation of energy. I want to imagine I take something round and with a measurable radius and roll it down a ramp. This could be a roll of tape. It could be a basketball or some other type of ball. Really anything that I just set at the top of a ramp and let it roll down. We should be able to use energy to think through a situation like this. At the very top of the ramp, whatever object I put on there should have a whole bunch of gravitational potential energy, where gravitational potential energy is mass times little g, which is that 10 newtons per kilogram, times the change in height, where that height is going to be, if I were to find what height does this object end up at, and then measure how far above there does whatever I'm rolling start. The other type of energy we would pay attention to is kinetic energy. And if I just set this object down at the top of the ramp, it starts out with no kinetic energy. And then what I would do is say at the bottom of the ramp, I'm going to set that as a height of 0, since that's where I'm measuring my height from, which means at the bottom, all of the energy is kinetic and there is no gravitational potential. What that means for the math is that the gravitational potential at the top should equal the kinetic energy at the bottom. Here's the trick. If you were to actually go out and make these measurements, you would find that the actual v, the actual velocity, is much, much smaller. So this is predicting a much bigger velocity than we should get. And it can be a difference by as much as 60%, which tells us it's not just uncertainty. It's something we're not accounting for. It turns out there is a form of energy that we haven't dealt with yet that's really important in this case. And that's rotational kinetic energy. On your formula sheet, on the left side, pretty close to the bottom, is this formula right here, which actually looks pretty similar to the formula we used earlier this year for kinetic energy. Earlier this year, we had 1/2 mv squared, where m is that inertial mass, so how difficult it is to change the object's motion. Now with rotational kinetic energy, we have rotational inertia, which is that capital I. And then instead of linear velocity with a v, we now have angular velocity with an omega. So that's how we would find rotational kinetic energy. Now that we have this formula, I can actually do some more accurate bar charts for this situation. So once again, I'm going to assume it starts with all of its energy as gravitational. If it's at rest at the start of, or at the top of the ramp, then that checks out. And then the bottom of the ramp, I'm going to treat as a gravitational potential energy of 0. Now I like to add little subscripts to these kinetic energies so I can keep track of which type of kinetic energy I'm talking about. I'm doing kinetic energy with a little L for linear. And then I'm going to add a third bar or set of bars, and that's going to be my rotational kinetic energy. And so this is essentially accounting for that motion of the object turning. So it's spinning and rolling as it moves forward. So that linear kinetic energy is related to the speed of the center of mass, but that rotational kinetic energy is related to how fast it's rotating. And I can right away see from my bar charts that when we're accounting for that rotational kinetic energy, I've got less linear kinetic energy than I originally predicted, which would match with getting a smaller linear velocity. And I can set up my math a lot like we set up conservation of energy equations in the past, where again I'm replacing each form of energy with its equation. So instead of linear kinetic energy, I'm doing 1/2 mv squared. And then instead of rotational kinetic energy, I'm going to put our new formula, where I, again, is that rotational inertia, so how difficult it is to change the angular motion, and then omega is the angular velocity. So that's the big stuff you need to know about rotational kinetic energy.